Welcome to Study Loop.
So now we'll work on problem 61 from chapter 5. In this problem, we're asked to determine molecular geometries for several molecules and then draw their structure using the conventions shown in this chapter 5. So we can start with our first molecule, SF4. We have 28 electrons from fluorine, 6 from sulfur, so we have 34 electrons in total. Sulfur is our center atom. We have 4 fluorines surrounding it. Bonding these 4 atoms takes up 8 electrons, so we have 26 left to assign. We assign 6 to each fluorine atom as lone pairs, which takes up 24 electrons. So we now have only 2 electrons left to assign, so we give them to the center atom. So here we have a molecule with 5 electron groups. However, only 4 bonded atoms. So for 5 electron groups, the electronic geometry is trigonal bipyramidal. However, if we remove one of those groups, the sulfur, it will be, we remove the lone pair from the sulfur for the molecular geometry. That's going to come out of the center atoms, the triangle, not the ones on the top and the bottom. And so we're going to have a seesaw structure. And how we usually draw that, or draw sulfur as a center atom, we keep the top and bottom atoms, but we lose one from the middle. So now we have one going in and one going out. So if we were to flip this on its side, it would look like a seesaw. So we can move to part B now, where we're given ClF3. All of these are halogens, so 4 times 7 is 28 electrons. So chlorine will be our center atom. We're going to surround it with 3 fluorine atoms, which takes up 6 electrons. We assign 6 electrons to each fluorine atom, which takes up 18 electrons, which leaves us with 4 electrons left, which we assign to the center atom as lone pairs. So again, we have 5 electron groups, 3 bonded atoms and 2 lone pairs. But this time we have 1 less bonded atom. So we're going to have to remove another atom from this, the center, the triangular center of this trigonal bipyramidal structure. And so instead we have T-shape as the molecular geometry. And so this one here is a little easier to draw because we can draw it all in the plane of the paper. So we have a fluorine above, we have a fluorine below, and then we have a fluorine to the side. Here and here are the lone pairs that we took out, but we don't draw them in the molecular geometry. So in part C, we're given IF2 minus. From the atoms, we get 21 electrons, and then we get the 22nd electron from the negative charge. Iodine is our central atom. We bond it with 2 fluorine atoms, which takes up 4 electrons, leaving us with 18. So we assign 12 as lone pairs to the fluorine atoms, which leaves us with 6 electrons left over. So we assign all of them to the center atom. We again have 5 electron groups, 3 lone pairs and 2 bonded atoms. So similar to what we saw previously, so first we had the seesaw, then we removed 1 more atom from the center and got a T-shape. Now we're going to remove this final atom from the center and we're going to get a linear structure with just iodine and fluorine. So that's the molecular geometry for this molecule. And then finally in part D, we have IBr4 minus. We have 36 electrons here, 35 from the halogens, 1 from the negative charge. So we have iodine as our center atom, 4 bromine atoms bonded. That leaves us with 28 electrons, so we assign 24 as lone pairs to the 4 bromine atoms, which leaves us with 4 electrons left over. So we assign 2 lone pairs to the iodine center atom. So this time we have 6 electron groups, which is octahedral. However, in the octahedral structure, the first atom, the first group which we take out doesn't matter because they're all equivalent. But once we take out the first one, then we need to take out the one that's farthest away from it, and that would be the one on the bottom. So that's going to leave us with a square planar structure. So we can draw this in the plane of the paper as well. There's also another way to draw, which I'll show. So the lone pairs would be on the top and on the bottom in this drawing here. Maybe a more clear way to represent is by showing 2 atoms going back and 2 atoms going out. In this case, the lone pairs would be here and here, but again, we don't show on the molecular geometry.